Is there anyone from ISIEINDIA?
Yes, sir, we are recording.
Thanks for the confirmation. Okay, so let's continue. So, what are the control systems and why should one study them, right? So, when we look at the control systems engineering, what we do is we design and we analyze systems for performance and stability. So, performance and stability is what we are interested in. We basically what we do is we define and tweak our system to meet our objectives. And what could be our objective? So from performance, right, achieving a particular position or achieving a particular speed, achieving torque, achieving force, achieving a temperature or a flow rate. are the performance criteria. These are our objectives of the control system. From stability criteria point of view, what are the objectives? From stability point of view, all we want to ensure is throughout the operating range, our system should stay stable. It should not go out of bounds. This is where the Bibo stability theorem comes into picture. We know Bibo theory from the control systems, right? Now talking about some of the myths that there is this general idea, especially in the students, that control systems are inherently very complex and control system theory is very difficult. The myth is there because of the math that is involved in control systems. It involves rigorous math, and the reality is the complexity of a control system really depends on the type of system that we are controlling.
Hello, sir. Hello.
Hello. Hello. Am I audible now?
Yeah, continue. Sorry.
Could you please tell me till when I was audible last? Should I repeat this slide?
Yeah, please repeat. Yes.
Okay, sure. So, let us see that what are these control systems and why we should study them. So, control system engineering has design and analysis. Why we do the design and analysis is because we want to achieve a particular performance and stability. And what we do in control systems is basically define and tweak these systems to meet our objective. We have two objectives, one is performance and another is stability. Performance means achieving a particular position, particular speed, particular torque, particular force, temperature, flow rate, etc. On the stability side, what we want to achieve is a stable system throughout its operating range. From stability point of view, the Bibo stability, bounded input, bounded output theorem is very useful and it is widely used in the control system. Now, there are certain myths about control systems that control systems are very complex and control system theory is very difficult. This is so because control system theory involves a lot of mathematics. It is mathematically very, very rigorous. However, the reality is that the complexity of a control system really depends on two things. One is the type of control system, the type of system that we are controlling, which is nothing but the physical system or a plant. In an electric vehicle case, the whole electric vehicle is the plant. And no doubt about it that it is very complex. The another thing it depends on is the control technique that we are employing. If we say that our control system, our plant is very highly non-linear and we want to develop a non-linear control system, then yes, this system would become very complex. But on the other hand, if we were to linearize our non-linear control system into something called as piecewise linear control system, then the control system or the control technique that we will use then becomes simple. I hope that is clear. Moving on to the next slide. So let us discuss how one can design a simple closed-loop feedback control system. So we know from our control system theory that for any control system we should have a controller, which is nothing but here. This controller will be sending out some control effort depending on the error which is being calculated. This control effort will go to something called as actuator, which is nothing but a device which takes energy in and it converts it into some other form. It could be that it takes electrical energy inside and gives out something like force or a torque. This actuator output goes to the plant. In our case, this plant is vehicle. When vehicle gets torque from something like motor can be an actuator, then the vehicle is propelled forward. Right? Then we have sensing. We could be sensing, let's say, speed of the vehicle, and that speed we might be using in our controller to maintain a particular speed. A typical example would be a cruise control system, or even a human being trying to control speed of the vehicle. On the reference side, we always have a set point or a reference or a desired value, which is what we would ideally want. And how we control the system is we have this sensor output, we call it actual value or measurement, or it could be an observer estimation. We use these two information to find out the error. So we subtract the sense value from the reference value to get notion of how far we are from where we actually want to be. We use that information to calculate this control effort, and so forth. This loop continues. And because we have a sensor in feedback loop, this is the loop, we call it closed loop feedback control system. These control systems are very common, and most of the electric vehicle systems that you see, this is how the control system architecture would look like. So now that you have some idea about control systems, let's talk about what are these control systems, and again why we should study them. So in control systems engineering, it's a very broad field, and there are complex applications. We just saw automotive example, but similarly we have biomedical, home appliances, power tools, aerospace, space technology, trains and marine systems, food processing, defense systems, assembly line and automation, precision manufacturing, robotics, and many such more, right? Alright, so now let's move on to examples of control systems in automotive application. So this is why we are here today, right? So far we have only been building some ground, we have only been building some momentum. Now we will deep dive into the actual control system that we are interested in. So this is where I want to know from audience. Could you please, maybe you can put your answer in the chat window. What do you think are control system for automotive application, especially from electrical vehicle point of view? I would love to read your answer. Please type them out. In the meanwhile, let me continue. Yeah, that is correct, electric drive unit. Please go ahead and put it in the chat window so that we can, in parallel, we can continue with the PPT. When we talk about examples of control systems, so we know that in automotive we have different type of vehicles. We have a traditional vehicle, we have electric vehicles, we have ADAS, and we have autonomous vehicles. So each of these different type of vehicles will have their own set of control systems. What we have listed here are all different type of control systems together. So we have steering control systems, then we have throttle or cruise control systems, then we have brake control systems, transmission control systems, engine control system, transmission control systems, then electric drive control system, and battery management control system. Now, if we look at the picture, what we see is we have Suzuki Alto vehicle, let's say it's a petrol-based vehicle, so this is the conventional vehicle or a traditional vehicle we usually talk about. Then here we have Tesla Model S. This is an electric vehicle, it's a pure, strong EV. Here this is a MG Hector this is Astor vehicle from MG, and this vehicle has certain ADAS features, advanced driver assistance features. Well, this is a Waymo vehicle, also called a Google car. This is a completely autonomous vehicle, and all these vehicles use one or many of these control systems. So now that we know what are the applications of in automotive for control system, let's deep dive into electric vehicle control system. So electrical vehicle, this is very obvious, right, that we will have electric drive control system, inside electric drive we will have motor control system. We will also have electrical brake control system, which can also be termed as a regenerative braking in case we are actually regenerating power from the vehicle. Another control system is battery management control system. In battery management control system, we have charging control system and we have discharging control system. Discharging control system means we are actually powering the vehicle, and charging control system means we are recharging the battery. Apart from electric drive control system and battery management system, we will have something called as vehicle control unit, body control unit, chassis control unit, brake control unit, and powertrain control unit. These systems are required for correct operation of the all the other subsystems of the vehicle apart from electric drive system. And in fact, these are also the same systems which you will see common across most of the other vehicles. So in traditional vehicles or conventional petrol or IC engine based vehicle also you will see most of these functions. Alright, so now let's discuss about electric drive control system. So we just saw one control system which was a very simple control system. We can look at the electric drive control system from same perspective. The only difference is in electric drive control system has two closed loop feedback control loops. So here we can see one loop, the bigger loop, and another is a smaller loop. So why we need this loop is as a driver is generally interested in speed control, right? When we travel in a vehicle, what we generally are interested in and what we perceive is speed. We don't generally talk about torque. So when a driver is driving the vehicle, what he or she has in mind is that I want to go at, let's say, 60 kmph speed. What would the driver do? Driver will press the acceleration pedal. When he or she presses acceleration pedal, whatever propulsion system is, the system will produce the desired torque. So here we have driver and the driver has a desired speed. So driver will give input on the acceleration pedal and from there a desired torque will be intimated to the motor controller. Now this motor controller will look at the desired torque. It will look at the actual estimated torque in the system, and if they don't match, it will produce phase voltages. These phase voltages will be applied to the motor. Now this motor will eventually exert torque on the vehicle, and this is how the vehicle is going to be propelled. So now let's look at each control loop one by one. Let us first discuss about this larger loop, where essentially what is happening is driver is asking that I want to move at so and so speed, and then he is just looking at the actual vehicle speed from this loop. So we have a speed sensor here, vehicle speed sensor. This feedback goes to the speed controller. This controller is in fact for a manual vehicle, I mean a vehicle which is not working in a cruise control mode. This speed controller happens inside driver's mind, right? So we see that the speed is not enough and we press more acceleration pedal. So that control system is actually happening inside the driver's mind. So that is how the outer loop is working, which is nothing but the speed control system. The inner loop is more interesting and it is in fact one of the critical control systems, which is about achieving the required torque. So motor receives torque as input from the speed controller, and inside motor controller we have very complex logic. We have many logic from torque production to fault diagnostic and lot of other things. But essentially what motor controller will do is will look at what is the required torque, it will produce the required voltage, and it will give those voltage as input to the motor. The motor is part of the plant, it is a physical system. When it is given certain voltages, certain currents are produced, and these currents produce torque. Now here there is something very interesting. If you were to see these two loops, you will say that here we are seeing speed, we are sensing speed of position using the speed sensor, but here why are we sensing current, right? Even though we want torque. So why this happens is torque sensors are very costly. Torque sensors are also difficult to implement on a vehicle. This is why current sensing is used and torque is always estimated from the measured current. Why this works is current has pretty much a linear relationship with torque and it's a very direct relationship. Higher the current, higher the torque. So that is why we have something called as a torque observer instead of a sensor. What we really have is a current sensor and then the sensed current is used to estimate torque, which is why we are calling this an observer. This observer is also a very important and very popular concept in control systems. I'm assuming that you are already aware about the observer concept. So this is how this inner loop is working, and this is sometimes, so there are different ways to model this loop. One can have a parallel control system, one can have a series control system. Generally, this control system is used for vehicle speed control. Now let us look at how this electric drive control system looks like from logic point of view. So if there was a main state machine, state machines are very common in control systems, especially when we have different states of a vehicle. In our case, for electric drive control system, we can have at a broader level, we can have 4 states. One could be the idling. Inside idling, we are not doing much. We have just have ignition on for the vehicle, but we are not driving as such. But the moment we see that there is power demand, what we do is we go inside motoring state. So this is where from idle state we are transitioning to motoring state. From motoring state, the system can go to regeneration or electrical braking if it is negative torque. If it is zero torque, it will go back to the idling state. Similarly, in regeneration or electrical braking state, if it is positive torque, it will go back to motoring because it means that we want to go forward. If it sees that we are still in a negative torque zone where we are basically regenerating, it will continue to stay in the state. And if we see zero torque, it can go to idling. Now there is a common state, something called as fail state. Fail-safe state. Fail-safe states are useful whenever there is a fault in the system. We want the system to be in a safe state. So whenever a failure happens, we would like to detect the failure and we would like to come inside this fail-safe state where we are taking certain precautions and we are acting on certain inputs from the system so that the overall vehicle remains safe and the passengers also remain safe. So this is how a very broader level, higher level state machine would look like for something like electric drive control system. And on the left side, what you see is essentially a system block diagram. So in the center we have these are the peripheral systems which are providing inputs. For example, from driver we get acceleration pedal input, which means if the conditions were to go out of the safe region inside which a lithium-ion battery is supposed to operate, if such a thing was to happen, then it could pose a hazard to the vehicle, to the passenger, as well as to the surroundings. And we don't want that to happen, which is why we need a supervisory control over this battery so that we can control its temperature conditions, especially the temperature conditions. And how it is done is by constantly monitoring current, voltage and temperature of the battery. While BMS does this, BMS also broadcasts important information such as what is the maximum discharge current, that the battery can afford, and accordingly something like electric drive system will ask the motor to produce torque. So it uses information from battery management system to limit its operation. Alright, so if we were to look at a block diagram for a battery management system, what we will see is we will have our vehicle load demand. So this is nothing but our sort of a reference. We can call this our reference. It goes into BMS controller, and then BMS controller will be essentially talking to this battery plant, which will be placed which will actually be placed inside a vehicle, and there will be discharge current, charge currents. Because of this, BMS will have to constantly run some algorithms, which are, for example, SOC algorithm, which is state of charge, which tells how much more charge is available, which also is used to estimate vehicle range. Now, from battery plant, we will have some sensors. So voltage and current sensors will be there, which will be sending voltage and current information to the BMS. Then we will also be having temperature sensor, which will be sensing temperature of the battery and pushing it to the BMS, so that BMS can take an informed call. So there are various functions which BMS performs. Apart from charging and discharging, BMS also performs, like we just discussed, the SOC estimation, cell balancing, current cutoff in case there is a short and high current is flowing through the system. It also takes care of certain faults like overcurrent and over voltage, under voltage faults. So largely BMS works around these functions. If we were to look at a higher level logic for battery management system, what we will see is there are largely 4 states. One is idling, then we have discharging, we have charging, and we have fail-safe state. So whenever we see that positive current is being demanded, we go into discharging state from idle state. When we see that battery is being charged, it could be through a charger, it could be through regeneration, motor regeneration. Then we go into charging state, and at any point if we encounter a fault could be overcurrent protection fault, it could be under voltage protection fault, or over voltage protection fault. Then we go into something called as fail-safe state. Fail-safe state will ensure that the battery, vehicle, passenger, everyone is safe whenever such a fault occurs or some failure occurs. I hope this gives you a good idea about what all components are there in a battery management control system and how a top level logic would look like. To give you a better idea about control system, now let's dive into the demonstration of a battery management tool called as Collimator. It's a Python and cloud-based tool for model-based design, and I hope this will give you a better idea about battery management system. So let us go into it. Please give me some time to pull up this tool. Please let me know if you are able to now see my screen with collimator tool.
Yes, it is visible.
Right, thank you. So this is a collimator tool. In collimator tool, we have canvas. So this is the canvas. This is where we do our design work. We also have something called as library and model tree. So we have library of all the different blocks here. We also have a model tree here, which basically lists all the blocks used in the model. Let me hide this so that we have a better view of the control system. On the right side, what we have here is we have model properties. So we have description, certain model parameters that we are using inside our model. And here we have simulation settings. We also have something called the version history. So this collimator tool automatically saves the version history of the model. Let me hide this so that we have a better view of the model. So I hope you are able to see the screen. I hope you are also able to see the model properly. Are you able to read the components now?
Yes, sir, can be.
Thank you. Thank you for your feedback. Now let's go into each of this model one by one. So let's first look at the vehicle load demand. So how does a vehicle load demand look like? It basically looks like a pulse. Why we are emulating it as a pulse is because when a vehicle is being driven on a something like Indian road cycle, Indian drive cycle, we will be accelerating and then decelerating, which means that we will be discharging the battery and then we will be charging the battery for some time. So that is why we are using a pulsed control system, a pulsed block set to generate this demand and emulate a vehicle load. In reality, how this will happen is we will have a motor and inverter, this electric drive control system, and that will be sort of generating this vehicle load demand. Now this goes into BMS controller. Why we are currently sending it to the BMS controller is so BMS controller will be controlling this current by informing the motor controller that how much current it can draw. Sorry.
Am I audible?
Yeah, you're audible.
So, what is the application name?
It is collimator. COLLIMATOR.
Okay.
All right. So now coming to the monitoring part. So we have something called as cell current monitor. So what this control system does is it converts the measured current through the hardware circuit into the engineering value. And this engineering value will be in terms of ampere and it will be further used in the control system. As part of monitoring system, we also have something called as voltage monitoring control system. So voltage monitoring control system also what it does is it measures the voltage from the hardware, electronic hardware, and it converts it into engineering value. Now the current that is measured is basically used to estimate vehicle SOC, battery SOC, and here we are using simple Coulomb counting to arrive at a battery SOC. Battery SOC is nothing but state of charge. And then we have a temperature monitoring system very similar to current and voltage monitoring system. In a BMS system, one can also have other more features, for example, cell voltage balance and cutoff FET. Cutoff FETs are to ensure whenever a high current is passing or a high voltage is observed, which could potentially damage the component, we cut off the path. Essentially, we isolate our load from the battery. Now coming to the battery plant, so how a battery is modeled here is essentially battery So in reality, what happens is we either discharge or charge the battery, and accordingly the SOC of the battery changes, and the closed circuit voltage of the battery changes, and the temperature also accordingly changes. So here what we want to do is we want to look at the current which is there in the system, whether it is charging current or discharging system, or discharging current, and we want to use that along with battery data. So we have battery dynamics here, battery circuit, and some battery data from SOC, and open loop open circuit voltage data is being used to estimate what would be the battery voltage from because of the charging and discharging of the battery. So this battery gives out SOC energy and cell voltage and temperature, and this is eventually used. This is basically used to this is basically sensed, and then the BMS takes the action. So I hope you got some idea about how battery management system works with battery plant, and how they are generally designed in something like model-based environment. I wanted to show this demo so that people feel more connect to how actually the systems are modeled and simulated. These are representative systems. Actual systems which go onto vehicle are far more complex. They are far more detailed. There are far many features. So yeah, overall that's it about this demo. What I have here for you is, if someone is interested to try out this tool, please feel free to connect with me, or you can also use the Google form that I'll be sharing as a part of feedback, to share your details and share your interest, and I will try and make this tool available for you. It's a very interesting tool. It's a web-based tool, which means it does not require any installation. All it requires is a browser and internet connection, and it's a very good tool to learn model-based design. Alright, so now let's go back to our presentation. We have about 15 minutes, so I'll try to finish in next 5 minutes, and then we can have a question answer session. Please let me know if my screen is now visible.
Yes, sir,
Yeah,
it's
it's
visible.
Thank you, sir. All right. So that's it, guys. I hope this session was useful to you. I'm open for question answer, and also for the feedback. For feedback, what I will do is I'll share a link to the Google form, and you can share your feedback there. Or Amol can also forward your feedback to me, whatever works best.
Yeah, sure. What I will do, I'll share one feedback from with all of them, and then that I can share with you.
Sure.
Hello, sir.
Yeah, please tell.
Sir, can you once more show that motor control system? Sorry.
Yeah, just a minute. Let me quickly share this link.
For the motor, not for the BMS.
Understood. But I'll do that in a minute.
Okay.
Yeah, please use this link in the chat window, or get back to me through Amol. Alright, so let's go back to the motor control system. Yes, this is the system. Can you please confirm that this is the slide you want me to go to? I'm sorry, I didn't get your name.
Yeah, we need. Yeah, this is the one, sir. Now I
understand.
Sorry.
Yeah. Please tell me. Is there a question?
This is the one. This is the one.
Okay.
Okay.
All right. Do you have some question or some query here?
Yeah, because we are changing the current frequency or the voltage to the motor for controlling its speed and torque, right?
Correct.
Okay. Or there is any PW impulse with modulation like that?
True. So in fact, this is a very broad level control system. In reality, what you will have is between the motor controller and the motor, you will have something called as inverter or a controller. Converter. Yeah. And this inverter will be basically it will be powered using DC power from the battery, and it will be generating these phase voltages, which will be essentially a AC power for the motor.
Yeah.
And when we use techniques like field oriented control, we need to use space vector modulation, and all that will be happening inside the inverter. So your motor controller will only be sending information like
the throttle input like that, so that they can perform.
Yeah.
Okay. Yeah, most of the EVs are fitted by AC PMSM, AC permanent magnetic signals motor. Even the I think the Porsche Taycan also. So I don't know why the manufacturers are biased to the AC synchronous. They are not one for the DC.
So brushless DC and PMSM are very commonly used. You'll also see induction machines and even in some cases switch reference machines. So these are AC machines essentially.
Okay.
Yeah.
Okay, sir. Okay, it's all.
Okay. Thank you.
Sir, is there any way to get this PPT for reference, sir? Do you share this one?
I will discuss with Amol and then Amol.
Okay. Thank you.
Okay.
Okay, sir.
Excuse me, sir.
Yes.
Sir, I have a question. That is there any control system in Tesla car or Waymo car which makes it to drive in an autopilot mode?
In Tesla, yes. Tesla has autopilot.
Is there any control system, special control systems is there?
So it's basically an autonomous vehicle. So autonomous vehicle will have perception control system. Right. For autopilot, what we need is perception information. For example, what is the surrounding, what is the environment, where is the road, are there any pedestrians on the road, is there a vehicle in front of you, right? We need to perceive it. So this has to happen automatically, right? As a driver, we see and then we take decisions. For autopilot systems, perception has to happen. So there are perception systems which basically observe the environment, and then you have a tracking and planning control system. So these systems basically track where the vehicle is going, and they plan for how they want the vehicle to go in future. And then you have this control system like electric drive control system, and then battery management systems, which actually take care of the actual movement of the vehicle. For example, you can have a motor which is driving the vehicle. So once a decision is made that whether you want to go left, whether you want to go right, whether you want to brake or you want to accelerate, accordingly the decision is taken. So autopilot is the overall system which is doing a lot of functions of roughly one can say that it's doing functions of a driver, right? It's a pilot basically. It is doing the driving work. So it will have a lot of such controls. It won't just have one control system.
And what powertrain control system actually does?
So powertrain is, if I was to give you an example of a conventional vehicle in a powertrain, one can say that the engine plus gearbox plus the axle system till the wheels, that whole thing comprises as a powertrain system. So for that powertrain, you can have a powertrain control system which will basically control your engine, and it will also, if your vehicle has automated transmission or some automatic transmission, then same powertrain control system will also control the gear actuation, then clutch actuation, you know. So powertrain control system will be largely around the system which is essentially propelling your vehicle. In case of conventional vehicles, we have engine and clutch transmission. In case of electrical vehicle, we have electric drive control system. So electric drive control system will be part of the powertrain.
Yeah.
I hope this answers your question.
Yes, I understood. And one more question is there, that is last whatever the application you have shown us, in that application, what is the name of the application?
So we discussed two examples. One. Oh, you are talking about the tool.
Yes, I'm talking about that too.
Okay. Its name is Collimator, COLI LIMATOR.
Okay.
You can use the online form to refer to it if you want to do it in the future. You can share your interest through this form. And
yeah, I'm interested to do some design on this.
Sure. Please go ahead and fill up the form, and I'll definitely get back to you.
Okay. And can we design as well as simulate within this application?
Yes, it can be simulated. However, the simulation, this model especially runs for approximately 4 to 10 hours, and that is why I did not simulate it right now. So I want to do simulation for 4 to 10 hours, and it might generate a lot of data right now, which is why I did not go ahead and simulate it, but it's a model plus simulation tool. So you can go ahead and simulate your control system. It could be a motor model, it could be a battery model. It's very much like MathWorks simulation.
So I can design my own control system, right?
Yes, you can design your own control system, you can design your own plant models, you can design your own logic, you can design your state machine. Yeah.
Okay. So just send me the form in the chat box. I will fill it up.
Yes, I have already sent the link. I will paste it again for everyone's reference again. I hope it is accessible to you.
Where you have given, sir? I have still not get yet.
Okay, maybe Amol will get back to you on this.
I have got it, sir.
Okay.
Yeah, so I'll do one thing. I'll share the details with them once we complete the webinar.
Sure. That would be great.
Yeah.
Over the chat box. Hello.
Yeah, Shubham, we will share an email with you tomorrow for the certification and the feedback. So in that you will get all the details for the same.
Okay, clear.
Yeah.
All right, then we are reaching our time. I think we have 5 more minutes, so we can either continue with question answer, or if there is something else, we can do that also. Amol, did you have any input on this?
Yeah, participants, if you have any queries, you can ask.
I think think I saw a few inputs in the meeting chat. Okay, good. People have answered well about vehicle control units and yeah, battery, motor controller, trip, ECUs are there.
Just someone is asking, is there same tools used in MATLAB as well?
Can you please repeat?
It is. Someone is asking that do we have the tools in MATLAB as well for this simulation and control system?
Yes, MATLAB. So MathWorks has MATLAB and Simulink, and Simulink also has a lot of libraries. I hope.
Yeah, I think with the help of MATLAB also we can design the control systems.
Yeah, true. MATLAB is being used for quite many years.
So one more question is there, does there any possibility to use liquid cooling system in BMS?
So,
Good question.
so at architecture level, yeah, this is a very good question. I think this is from the point of view that we basically want to cool the battery, right? If the battery gets heated up. Traditionally, how it happens is not. So we have a separate cooling system which cools down not just the battery but also the motor and the inverter. So the cooling function generally happens through this cooling system, not through the BMS. I hope that answers your question.
Nice, well, I think.
Yes. All right. If there are no more questions, we can conclude.
Can you drop the call?
I hope. Yeah. So I hope this session was useful to you. Please feel free to give feedback. Also, if you are interested to try out to call in later, please let me know. Yeah. Thank you very much.
Thank
See
you.
Have a nice evening. Bye.
So for the participants, we'll be sharing you the feedback form and the registration form if you want to have that software that is pre-licensed from Sir. So I'll be sharing the details with you by tomorrow. So be in connect with me if you want to have. If you have any query, you can find my number in chat box. You can reach out to me. And we'll be sharing your feedback form with you by tomorrow for the certification. Actually, that is certificate mail and the feedback form will by tomorrow. Okay. If you have any query, you can reach out to me on the number. The number is given in the chat box.
Okay.
Yes.